Hi, folks. Today we're going to talk about the fundamental number sets. Shouldn't be too bad. And so in math, we often look at different collection of things. We call these collections sets. These sets could be numbers or sets of anything. And when we introduce the idea of set theory, we will go much more in depth into the idea of sets. For now, we want to focus on numbers because numbers are something which we often associate with math and we tend to play with a lot in math. So in the case of numbers, there are a handful of number sets which are foundational to our understanding of most areas of mathematics. Often numbers or branches of math will be linked to one particular set. For instance, in discrete math, we deal with countable number sets. If you're talking about complex analysis, well, we focus on complex numbers. And so let's learn the fundamentals. Our first number set is the natural numbers, and they are a very nice number set. They begin with 1, and then they count from there. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, you get the idea. There is no highest natural number, and 0 is not included as a natural number. Generally, we think of these as the things we deal with the most in the real world. How many of something do we have? So, yeah. We do have a symbol for it, and it is a fancy looking N, which looks like it has 2 lines going across the middle. And so you'll see that type of symbol pop up a lot. Next up, we have the whole numbers. The whole numbers are almost the same as the natural numbers, but they begin with 0. And so 0, 1, 2, 3, 4, and so on. With the introduction of 0, more algebraic techniques are opened up. And so 0 is sometimes considered the identity element. We can add 0 to anything and it changes nothing. That's very valuable. Multiplication by 0 has major implications. The symbol we use for the whole numbers is this W, which has extra lines in it. The integers is a set of all positive and negative whole numbers. There is no smallest number, as there will always be a larger negative number. So it goes all the way up to positive infinity and all the way down to negative infinity. And this is the first time we're really dealing with things where our quantity example doesn't really make as much sense. You can't have a negative number of burritos. Doesn't make sense. And so we have to apply some understanding to it. And the application that we usually do is a debt. And so a negative number of burritos would mean I owe you some burritos. The nice thing about negative numbers, it makes it so that we can actually do algebra. Without negative numbers, we would have a very hard time doing algebra. Next set is the rational numbers. And so rational numbers are any number which can be written as a fraction with an integer numerator and a natural number denominator. There are a lot of these. And so this includes all integers. 5 over 1 is just 5. It also includes decimals that end, like 3.14. That's 314 over 100. Note that's not pi. This also includes repeating decimals. And so repeating decimals can be written as a fraction, like 0.027 with a bar over it. Well, that's 0.027027027 all the way out, and that's just 1/37th. And so this then raises the question, what is a number which isn't rational? We call them irrational numbers. And so an irrational number is a number which is on the number line, but it can't be written as a ratio of integers. In decimal form, these numbers go on forever and ever and have no repeating pattern. The first one discovered was the square root of 2, which is 1.414213, but it goes on forever and there's no repeating pattern. Pi is roughly 3.14159. E is roughly 2.718281828459045, and so on. It turns out there are more irrational numbers than there are rational numbers. For now, I will leave you to wonder, what does that mean? How can there be more irrational numbers than there are rational numbers when there's clearly an infinite number of both? Well, there's more irrationals. A real number is defined as any number on the number line. It's the combination of all rational and irrational numbers. We can think of this as kind of the set of all of the other sets combined. And so most math we do involves numbers in this set. Algebra, trig, calculus, all of it is just real numbers. There are other more specialized number sets designed to do specific things, but real numbers will get you pretty far. That said, let's talk about some of those other things. So the first set is the complex numbers. And often folks get to the complex numbers, they learn about them in algebra, and they're like, aha, I'm done. I've got all of the numbers now. You'll never have all the numbers. And so the imaginary number I, which is equal to the square root of -1, is a number which isn't real in that it's not on the number line. It's still a useful number though, and so the idea of it being real is really a bad name for it. A complex number is a number of the form a plus bi, where a and b are real numbers. And so examples would be 2 plus 3i, or 1 minus the square root of 2 times I, or 7. All real numbers are automatically complex numbers. And so much like negative numbers, we usually need to apply some meaning to complex numbers. And there's one meaning which we usually see, and that is the idea of rotations. Complex numbers are able to give us a visual for rotating things, which is unlike anything else in math. And so whenever we need to model rotations, we will usually use complex numbers. Along with the complex numbers are the Gaussian integers. And so Gaussian integers are complex numbers of the form a plus bi, but where a and b are both integers. And so 3 plus 2i, or 4i, or 7 are all Gaussian integers. Complex numbers with fractional or irrational parts, so like if this were 1/2 plus 2i, that would not be a Gaussian integer. These are often used in mathematics. Whoops, went too far. These are often used in mathematics to understand more complicated algebraic structures. For example, in the Gaussian integers, 5 is no longer a prime number because it can be written as 2 plus I times 2 minus I. And so then the question becomes, can 3 be written as the product of two Gaussian integers? What values can be written as the product of two Gaussian integers? And what does it even mean to be prime in that context? And so these are bigger theoretical questions which are important to answer so that we can answer other things in physics, chemistry, and the real world. Our next sets are the algebraic numbers and transcendental numbers. And at this point, we're getting into some pretty complex sets. And so an algebraic number is a number which is a solution to a polynomial equation where the terms in the polynomial have integer parts. So the square root of 2 is considered algebraic because it's the solution of the equation x squared minus 2 equals 0. All integers and Gaussian integers are also algebraic numbers, but there are many radicals and other irrational numbers which may or may not be algebraic numbers as well. Numbers which are not algebraic are considered transcendental numbers. And so examples are e, pi, natural log of 2, or sine of 1. These can be very difficult to determine. It can be very difficult to determine whether a number is transcendental or not. And there are many open questions where there are numbers where we ask, is it transcendental or not? And we may have a suspicion, but we do not have a proof for it yet. And so one of the challenges is trying to prove those things. Final thoughts. Depending on the branch of math we're investigating, we'll be dealing with a different set of numbers. And so always keep an eye out for the types of numbers we might be dealing with. And if you're unsure, play around and see what makes sense. Consider exponents. How do exponents work differently between the different sets? So like, what does 2 to the 3 mean? What does 2 to the 0 mean? What does 2 to the -1 mean? What does 2 to the 2/3 mean? Or 2 to the square root of 3? What's 2 to the log base 2 of 3? Or 2 to the pi, or 2 to the I, or 2 to the 3 plus 2i? every single one of those has some different interpretation, some different meaning behind it. Can we understand what each one of those means? I'll leave you with that to think about. And so I'll let you go to work exploring where you find these number sets in the real world. Good luck, folks.